Good morning all. I think you would have gone through the first problem tutorial. Now I am going to discuss another problem. The problem is, I will read the problem. Again, absorption. An air stream containing 6 small % of ammonia is to be scrubbed with water. Scrubbing means absorption only. With water to recover 95% of the ammonia in a tower packed with 25 mm ceramic ration rings and operating at 20 degrees centigrade and 1 atmosphere pressure. The feed gas is supplied at a rate of 1000 kg per hour and the liquid rate is 1500 kg per hour is used. The equilibrium data is given for it is in mole fraction. The mole fraction of solute in the liquid phase, that is in the water phase, X is plotted against the mole fraction of solute, that is again ammonia in the vapor phase. That relationship is given us for different values. It is usually in this, it is given from the top to the higher value, the descending order. So when X is 0.095, Y is 0.091, like that. And 0.02, when X is 0.02, Y is equal to 0.015. This is the equilibrium data. Then you are asked to design the tower diameter. Design means to find the diameter height of the column. So you see the figure, it is shown here. Say packed column. There are two upper and in between two lines are shown. That is the up to this level packing. These rations are packed, and there are some spaces are left at the top, and some spaces are left at the bottom. And once again, I will repeat what are all the parameters. G1 is the mole flow rate of molecular flow rate of kilogram mole per second of the gaseous stream. Here it is air, and Y1 is the mole fraction of ammonia in air, which is 0.06, and G2 and Y2 are the after absorbing or after removing the ammonia, the air is going relatively pure air will be coming out of the column, that is represented by G2. And even though we say that it is relatively only pure, we will not be able to remove all the ammonia. So Y2 is the concentration of solute in the mole fraction of solute in the gas, which is going out of the column, and L2 is the liquid, that is here water solvent, which is fed into the column, and X2 is the concentration of ammonia. Suppose if in a plant you will be using used water after recovering ammonia from the water, the same water we are using, so there may be some residual amount of ammonia will be there. That is why we are telling it is X2. But in normal problems, we assume that the water which is being used is pure, so X2 will be 0. And then after absorbing ammonia, the liquid will come out of from the bottom of the tower, which is L1 and X1. These are all the notations. And G and Y, you see, G is any general location. It's any general. This is 1 is the bottom and 2 is the top. And in between, we call it G and L or Y and X without any suffix. So equations are usually represented in terms of X and Y using G and L. I think the description of the column is understood very well. I hope so, because this is the second example we are dealing with. Now let us go to the solution. What we are found out? What is to be found out? It's a packed column. So we have to select the packings. But in this question, here the packings are given. The packing specifications are given. That is 25 mm ceramic ration rings is used. So that is clear. You don't have, only thing is that you have to take the packing parameters from the appropriately from the table. Now next is you have to find out height. Height is given as for the gas phase. Height is height of packing is represented by NOG into HOG. NOG is the number of gas units or number of stages, and HOG is the height of the stage. And what is the unit of height of the packing? Millimeter. NOG is a mere number, doesn't have any unit, and HOG is unit of height. So height of the packing will be NOG into HOG. And next is you have to find the number of stages. There are three methods. One is graphically, the other one is using Kramser equation. Kramser equation can be used if and only if the reaction is dilute. If you want to use Kramser equation, you have to tell specifically that we are assuming the system is dilute at low concentration. So Kramser equation, for which and Kramser equation can be used if and only if the graph is, that is equilibrium plot is linear. There will be a relationship y is equal to mx. Then second one is equation for NOG. Then diameter can be determined by using empirical relations. Now you are familiar, you have already done it. And HOG also for empirical correlations. So this problem statement is over, and what are to be found is also clear, I hope. If you are not understanding, you repeat the play, and once again you go through it, and then it will be, you will understand it clearly. Now coming to the data. What is given? That is what is given? The feed gas is supplied at the rate of 1000 kg per hour, and liquid rate 1500 kg per hour. That is, so what is in mg, that is mass flow rate. What we require is in terms of moles. So the mass flow rate is 1000 kg per hour of gas and 1500 kg per hour for the liquid. So first we have to convert it into second. 1000 divided by 3600, that is equal to 0.278, and ml2, that is the liquid flow rate, that is 1500, that is equal to 0.412 kg per second. Then what else is given? Y1 is equal to 0.06. Then temperature is given 293. Pressure is 1 atmosphere. 1 atmosphere means you have to convert it into Pascal. 1 atmosphere is equal to 1.035 into 10 raised to 5 Pascal. Then we have to find the average molecular weight. Why? Because in absorption we use all the parameters on mole basis. Since it is in kilogram basis, we have to divide it to molecular weight. But molecular weight means which molecular will take in air. Some air as well as ammonia is there. So you have to take average molecular weight. Otherwise, you can see that it is 29 is the molecular weight of air and 17 is ammonia. If you find out the average will be 28.28. Or if you don't want to do it, you can write that since it is the ammonia is only 6%, molecular weight is, instead of taking average molecular weight, the molecular weight of air is taken, which is 29 also. And that is, to be accurate, you have to use the average, that is 28.28. Then mole flow rate you have to find out. What is G1? G1 is equal to 0.278 divided by 28.8, 9.82 into 10 raised to minus 3 kilograms per second. Then Y1 is equal to 0.06. GS is the solute free basis air. So G1 is the total amount of total moles of air as well as ammonia. But GS is solute, that is air alone. This is inert because GS won't vary from bottom to GS will be one and the same at the top and bottom. Why? Because air is not soluble in water. So the water will not absorb any air. So free air, the concentration or the amount of air will be, which is inert, will be constant. That is why GS will be constant. That is Gn into 1 minus y. How will you find out GS? GS is equal to G1 into 1 minus y. That is 9.82 into Y1 is equal to 0.064. So you will get 9.23 into 10 raised to minus 3. And LS, that is the liquid flow rate. Again 4.412 is in kilogram per second. That you have to convert into kilogram moles per second divided by 18, which is water. Now, so this is whatever parameters given in the question we have represented here, it's written here. One more information is given, that is, you have to remove 95% of acetone, isn't it? 95% ammonia is to be removed. So what does that mean? Y2 is equal to, will be, Y2 will be 95 into Y1. 95 by 100, 95, 1 minus 0.95, that is 0.05. But here you have to find out the mole ratio, not mole fraction. So you have to convert, capital Y1 is to be found out. Capital Y1 is equal to small y1 by 1 minus y1, that is 0.06 divided by 1 minus 0.06, it is 0.0634. Not much different, because this concentration is very low. At low concentration, mole fraction and mole ratio will be more or less same. So ammonia is to be removed is 95% of the inlet. So what will be left? 5% only will be left in the air. So 0.5 into y1, that is capital Y1, 0.064, you will get 0.0032. Then you find out the mole fraction, small y2 is equal to y2 by 1 plus y2. That's again also 0.0032 only, being a very small quantity. Then solvent is pure water, and x2 is equal to, that means x2 is equal to 0. Now you take a material balance of ammonia, because you can take the material balance based on the inert gas as well as inert liquid. Inert gas is air and inert liquid is water. So what you can do is, this is simple material balance, ammonia balance, Gs into y1 minus y2 is equal to Ls into x1 minus 2. Substitute, all the values are available. You find out except x1 can get that is equal to 0.0246. That means x1, that is capital X1, the amount of ammonia that is going along with the fluid liquid, that is solvent water, coming out of the tower is 0.0246. That is capital X1. You convert it into small x1, that is, you refer to the notes, and it is small x1 is capital X1. From capital X1 you can find small x1 as 0.0246 divided by, or capital X1 divided by 1 plus capital X1. It will be slightly less, small x1. So now you have to find almost every Gs is there, so G2 can be found out. What is Gs? Gs is equal to G2 into 1 minus y2, or G2 is equal to Gs by 1 minus y2. That also, so G1, G2, Gs, L1, L2, everything is known. Next is, we have to find the volumetric flow rate of end rings. Why do you require to find out the volumetric flow? Because you have to find the diameter. To find the diameter, what is the diameter is, sorry, not diameter, you have to find out area. Area is volumetric flow rate divided by velocity. Velocity you will be finding from empirical equations. So which volume will take, volumetric flow rate will take? You have gas as well as a liquid. So usually gas flow rate will be more. So you have to calculate that. That is why here, how to find out the volume. In the previous question, volume is given as in the question itself. Volume is given. That is volumetric flow rate was given. So you are finding the molecular flow rate from that. Here you have to. There are two methods. One is you use PV equals nRT. So V1 is equal to nRT by P. N you know, RT R you know, T you know. R table I have given. I don't explain again because it was explained previously very well. Then P, or you can find out, which will be more easy. You can take density of air from Perry. It is 1.29 kilogram per meter cube. That can be used, and find out that there is a small difference only. This is 0.23, the other one is 0.236. So you need me, if you can remember, but if some other gases are given, nitrogen or something like that, you may have to refer Perry and find out. Okay. Next is average molecular liquid, that is water. That you can see that average molecular weight is 0.9734 into 18 plus 0.026 into 17. That is more or less 18. That you can take, instead of calculating the average, you can take the molecular weight of water as such. Then you know the density of water, so you can find out the molecular volume, that is mass flow rate divided by density, that is 1000. We will get the volumetric flow rate of liquid. Now you have to do this. This is molecular volume is very less, whereas this liquid gas will have more volume. You should know. More volume will change with pressure. The higher flow rate of air is taken for calculating diameter of the column. Actually, I think I will have a break here. Let me see. So you have found out the volumetric flow rate. Next is you have the packing. You have to select the packing parameters, because in the previous question, in the sit-on problem, we have selected the packing. But here the packing is given. Packing to be used is ration ring, ceramic ration ring. So from page 1443 of 7th edition Perry or 1460 of 8th edition Perry, you can have the all parameters. That is 25 mm ceramic ration ring. The bed density is given, and what we require is this packing factor SP dry, which is 492 meter raised to minus 1. I have given a photo of this page. You take the corresponding page and see. Next one, we have to find out the number of stages graphically. For that, we have to plot equilibrium line first. Now, for the absorption, we have to use mole ratio coordinates. So, we have to convert the data which is available in mole fraction into mole ratio and then plot. It will be little bit difficult. For each value of x, you have to find out capital X, that is capital X is equal to small x by 1 minus x. Similarly, capital Y is equal to small y by 1 minus y. So you have to convert all data into capital X and capital Y and draw the equilibrium line. Then, but I have not calculated. I put it as small x and small y as a small fraction, and assuming that this is a dilute solution. So if you don't have time, you can write in the paper, even though it is not dilute, we are assuming it to be dilute, and then so mole fraction alone is used instead of mole ratio, so that the examiner will understand that you know the concept. If the equilibrium graph is drawn, and when you select the axis, you have to be very careful. But here it is straightforward, because for every value of x, the value of y is given, and the maximum is 0.09, and so you can take up to 0.1. But if it is linear and y equals mx, then you may make mistake. So you have to see what is the maximum value of concentration of solute. It is 0.06. So you can take some 0.0 to 0.1 and draw the graph. Now you have to mark B and A. Point B has got the coordinates as x1, y1 is equal to 0.04 and 0.06, and A, that is the top of the tower, which is x2, y2, that is 0 and 0.032. Now you have to mark A and B. Then B will be near to the A will be very near to the origin, and B will be away from the origin, because B represents the bottom where the concentration of the solute will be maximum both in the liquid and gaseous phase. Then you draw the join A and B. Draw this AB is the operating line, and then equilibrium line is already plotted. Construct triangles starting from B and then till you reach A. So number of triangles, count the number of triangles. I got it as 5. You draw it and check it. Now you think you will be very familiar how to do the counter construction number of triangles when finding out the number of stages. Next is using Clemser equation. It's also straightforward. Equation is given. You may have to by heart. And what is A? A alone is the fact which is you may not be very familiar. A is the absorption factor. It has got the formula to find out A is Ls by Gs divided by M. Ls by Gs is the slope of the operating line. Or in this case Ls and Gs values are available. So you can find out. So it comes around 2.5. M is the slope, you take the slope of the equilibrium line, initial slope, because it may not be straight line, initial portion only it will be straight. So you take the initial straight line portion slope and it is 0.75. So you calculate A, and then other things are everything is known, so you find out N. I got N as 3. Next is number of transfer units by the equation, that is y1 minus y2 by y minus y star Lm. This also you have to by heart, this equation, or you find out from Perry. It may be available in Perry. You find out the absorption chapter and then mark it and then take it from. Otherwise, this is a simple equation you can by heart. Here y1 is known. You may be little bit confused with the y1 star. That is, y1 star is the concentration of solute in the vapor phase, which is in equilibrium with the x1. That is, y1 is in equilibrium with x1. So x1 is equal to 0.024. So you draw a vertical line to meet the equilibrium line, that you extend to the corresponding value of y1 is 0.02. Next is, you have to all the parameters are known. You find out NOG, and I got it as 4. So you see that Kemser equation is it's an approximate equation. That is why we got 3. It is not correct because you are assuming that system is dilute and the equilibrium line is straight line. So that may result in some error, and then this equation also is not, using this equation also not correct. The best solution you will get from by plotting the graph and finding the number of triangles between the operating and equilibrium. Anyway, you have got it. For examination, you have to do only one. You select which is to be. If you can memorize this formula, make use of this. And I would like to talk about one more about the y minus y star Lm. So this is log mean temperature log mean concentration difference. Here also it is called drift factor. This will be of the order of 0.9596 like that. So substitute and find out. You have already found it. Okay. Next is, now you take N is 5 is the last, highest. Next, to find the diameter of the column. For that, you take page 1458 of 8th edition Perry. There is a figure 1455. It is written that FLG is in the x-axis. FLG is equal to L by G into rho G by rho L raised to 0.5. This is an empirical equation. See why it is an empirical equation? Because 0.5 is coming there. So this will be useful. It's really okay if only if you use the particular units, whatever specified. And Lm is the liquid mass velocity. That is, what is mass velocity? Mass velocity is equal to mass flow rate divided by area. So Lm corresponds to liquid. So mass flow rate of water divided by area, and you don't know area because you have to find diameter. So you take it as, because L by G, Lm by Gm you are taking, so you can, the ratio, it is a ratio, so that even though you don't know the area, it will get cancelled. So Lm is equal to 0.412 by CSA. Similarly, Gm, that is gas mass velocity, is equal to mass flow rate of gas divided by area. That is again 0.278 divided by CSA. Now FLG is equal to Lm by GS, Lm by Gm, and substitute, you get 0.05. Then using this 0.053 in the x-axis, find out from the figure. There are 4 or 5 lines are there. Each line represents pressure drop. So here I have taken as 1 inch per feet. So that you take, and then you will get the corresponding y-axis, that is 1.61. This is capacity factor. Capacity factor is, the formula for capacity factor is written here, and you know the capacity factor is equal to US. US is the superficial velocity into rho G and rho L are self-explanatory, and FP is the packing factor, and mu is the kinematic viscosity. So substitute all these things. Rho G you can find out from Perry, and it is 1.29 kilogram per meter cube, or you can calculate from PV is equal to nRT. I have written here and I cut it so that it is not just little bit tedious and lengthy. So if you are interested, you can go through it, otherwise forget it. Now the superficial velocity is obtained. Then you have to substitute FP is 492. You have already found out from Perry for ceramic crashing ring of 25 mm size. FP is the 492 and substitute. You get the US, that is superficial velocity, as 2.03 meter per second. Now you take 80% of it, that is 0.8 into 2.03, 1.614 meter per second, and G is already, you have find out that volumetric flow rate is whichever is higher, that is Vg, we call it V is the volume and G is the volumetric flow rate of gas. That will be higher than liquid. Liquid will be, volumetric flow rate of the liquid will be less. So area is equal to volumetric flow rate divided by velocity. Velocity you have already found out. Volumetric flow rate you have already determined. So this will give us a 0.146. Now you can assume 10% extra. So the actual area will be 0.16 meter square, and you find out the diameter using pi by 4 d square. You will get d as 0.45 meter. Radius is equal to 0.225. So here again we assume that you make it a round figure, which is 0.550 meter and 0.25 meter. Now this electrolyzer you have to convert and say the actual area, because you are using 500 mm diameter column. So you have find out actual area. So this is the area, diameter, everything you have found. Next is height of the packing. And height of the packing, you know, NOG into HOG. NOG you have already found out, that is number of stages. HOG you have to use empirical equations, that is given as G by KYA into 1 minus Y star LM. G is, here it's an empirical equation, so you have to be very careful about the unit of G. G should be in kilogram mole per meter squared second, and KYA is in kilogram meter cube, and 1YA doesn't have any unit. So you have to find out KYA is, and 1 minus Y star LM is defined here. This is called the drift factor. So you can find out this one. All the values are here. So this comes around 0.96. Now you have to see the how to find out the KYA. KYA has got the empirical relationship 0.0895, GM raised to 0.7, LM dash raised to 0.25. What is LM star? LM star is the mass velocity of water in kilogram meters per hour, and GM is the mass velocity of air in kilogram meters per hour. So this empirical equation is valid if and only if you use this units. Then the mass KYA is the unit of K kilogram mole per meter cube hour. So LS you have to find out, that is what is here is LS is equal to, LS already determined 2.28 into 10 raised to minus 2 kilogram per meter cube, but LM dash is, you have to convert it into mass units, so you have to multiply by molecular weight. So LM dash is equal to LS into molecular weight divided by A, that is 2.28 into 10 raised to minus 2 into 18, and 3600 corresponds to second, and 0.2 when you convert to hour it is multiplied by 3600 and then 0.196. So you get LM as 7538 kilogram per meter square hour. Similarly, GM dash as 5076 kilogram per meter square hour. Now you see that all the units are consistent. Here in the equation it is given what are the units to be used. Now substitute and you will get as 327.07 kilogram mole per meter cube hour. This is the value of KY. And 1 minus Y star, the drift factor is also can be determined. Now HOG, that is height of the packing, is equal to G by KYA into 1 minus Y star LM. Here G is the, again all the other things are in second. So you have to convert it into all the other parameters also into second. So KYA is equal to 327.07 kilomole meter cube per hour divided by 3600. You will get 0.091 kilomoles per meter cube second, and G is the value we have already found out here, because in kilo hour it is given, you have to find out in second. So now substitute it. Here simple substitution you get, that is 0.538 is the height of a stage. Then you multiply that by number of stages, you will get the height of the packing. Add 2 into 0.5 each, then you get 3.7 meter, it's 4 meter. You assume 4 meter length and 500 mm or 0.5 a meter dia column is used to find out this. So now I will stop it here, because one more method is the same way. There are two methods. So next, that is alternate method using empirical relationship, which is available in PERI. So that way I will. This problem is all over, because we have found out the number of stages, then diameter, then height of a stage, then the real height of the column. Actually, this is sufficient, but I am giving you one more alternate method to find out the HOG or the mass transfer coefficient KYA, because here you have used one empirical correlation. KYA is equal to 0.0895 5076 raised to 0.7 in this X. Otherwise, 0.0895 into GM dash raised to 0.7 into LM dash raised to 0.25. So it may be difficult for you to remember this formula. So another formula is very much equivalent to heat transfer operation. It is Sherwood number. What is you have empirical correlations in heat transfer, that is Nusselt's number is equal to, it's a function of Reynolds number and Prandtl number. Similarly, Sherwood number is equal to 0.023, RE raised to 0.83 and Schmidt raised to 1/3. Here Sherwood number is equivalent to Nusselt number, Reynolds number is one and the same, and Schmidt number is equivalent to Prandtl number. Schmidt number is a property of the fluid, Prandtl number is also property of the fluid. Now from this correlation, so it will be easy for you to memorize this equation. So you can make use of this equation to find out the mass transfer coefficient. So you substitute Sherwood is equal to Ky into dt by dAB. This is Sherwood number in the vapor phase, and Sc is the Schmidt number of the gaseous phase, that is air. And Reynolds number is that of the airstream. R is equal to dg by mu. D is the diameter of the tower, and dAB is the diffusion coefficient, and Ky is the mass transfer coefficient, mu is the viscosity. All the properties of the gas we have to take, because we are finding out the mass transfer coefficient in the gaseous phase. If you are using the mass transfer coefficient in the liquid phase, then you have to take the properties of the liquid. I will do one thing. I will give an example. I will do an example for you. How will you find out it using the mass transfer coefficient in the vapor phase, the liquid phase? So dAB is the that is diffusion coefficient of ammonia in air, which is given as 0.26 into 10 raised to minus 4 meters per second. Diameter is 0.5 meter, and mass velocity of the gas mass velocity is 1.41 kilogram per meter squared second. You find out the unit. You note the unit. Viscosity is 1.8 into 10 raised to minus 5 Pascal second. Rho is equal to 1.29 kilogram per meter cube. Reynolds number you got around 40,000. Schmidt number is coming at 0.53. I think when I was getting different answers, you check it. Maybe I don't know whether I have made any mistake in this. I got it finally 0.537. Sherwood number is equal to, you can get it as, if you substitute, you will get it 120.88. Now, SH is equal to Ky into dt by dAB. You can get Kya as 0.063 meter per second. Now you see the unit. But what the Kya unit should be kilogram mole per meter cube second. So to convert it into, you have to get kilogram mole per meter cube. What will you do? You will multiply by molar density. What is molar density? Molar density is similar to mass density. Mass density unit is kilogram per meter cube, but the molar density unit is kilogram mole per meter cube. So if you divide mass density by molecular weight, you will get molar density. And you have to find out the molecular weight, you have to take the average, or you can take the density of air, which is 29. Density of air is 29, and molecular weight is 29 into 0.94 plus 17 into 0.06, which is 28.28, or you can use 29 itself. CG calculate, it is 0.045 kilogram mole per meter cube. Then you multiply this KYA with the CG. Again, you will end up with, you see that it will be kilogram mole per meter squared second. So we have to get one more meter at the bottom, meter cube. So you multiply with the packing factor, which has got a unit of m raised to minus 1. You find out here it is 492 meter raised to minus 1. In substituting, you will get KYA as equal to 0.14 kilogram mole per meter cube second. Substitute in HOG and you find out the HOG is equal to 0.354. Then there are 5 number of stages. It will come around 1.73. You take top and bottom, some space, add it, and it comes around 3 meters. So you can see that if you are using these correlations, your design is different, and if you are using the other correlation, that is why we say the designs are not absolute. Different students may get different values depending, because it is your choice to select all the other parameters. I think with this example, you would have understood. So when you do it in examination, you have to find out NOG, you may have to follow only one method. Either among the 3 you can select one, and to find out HOG you can use one among this. So with this, I think you have understood the problem solution. Now, I will give one more problem that you have to do by yourself, and it is to be submitted. I will give a date that everybody should submit. Okay.